Well, what is NMR? NMR is nuclear magnetic resonance, and it is all about measuring the observed radio frequency within 4 to 900 MHz region by nuclei kept in external magnetic field. There are two catchy points in this definition of NMR. One is, unlike most of the other spectroscopic techniques where electrons are involved, here in NMR, nuclei is involved in the absorption process of the electromagnetic radiation. And the second point, the nuclei are to be kept invariably in the external magnetic field. Only then you can observe NMR spectrum. When you place magnetically active nuclei in the external magnetic field, the nuclear energy states separation takes place, and when you provide electromagnetic radiation which is precisely matching with the gap between two nuclear energy state of a particular nuclei, then there is a absorption and then corresponding resonance peak we can observe in the spectrum. The NMR phenomena was first experimentally observed by Felix Bloch and Purcell in 1946, and they have received Nobel Prize for their contribution in 1952. And believe me, with no time, this technique became so popular, and with no time commercially available, and many started using in their routine experimental chemistry. And nowadays, NMR is widely used as a preferred technique over many other spectroscopic techniques, mainly for structure elucidation of organic compounds. However, there are many other compounds we can also analyze using the technique to obtain specific information of magnetically active nuclei. Therefore, it is not only for organic compounds but also for inorganic and various other type of compounds as well. What exactly we get from NMR analysis? This is mainly to probe composition, structure, dynamics and function of the complete range of chemical entities. That means, so from small molecules to much larger molecular weight polymers and to proteins, all these molecules can be analyzed by NMR, and we can obtain the information and we can interpret to our routine experimental chemistry. Let me give a brief, little bit more details about the applications of NMR. Here there are 6 points that I have summarized. All these are major applications of NMR. The first point, NMR is generally used mainly for structure illustration of organic compounds. Initially it was, in the older days, many people were very much interested in natural products. So many of the natural products were characterized by NMR spectroscopy, and overall the synthetic chemistry, many people use NMR. And this is the favorite tool to analyze to find out the exact structure of compounds. And of course, this is not a complete technique which revealed the complete structure of a unknown molecular structure. It is always the case that the molecule structure of unknown is revealed only by combination of techniques. That is where NMR is going to play a crucial role, and when it is combined with the mass spectral data and also the IR data, we can get a complete picture of molecular structure of unknown compounds. This is an example of very complex molecule, Taxol. It is a natural product which is used for cancer treatment. This structure is revealed by NMR spectroscopy. Another major important application of NMR is it allows us to monitor certain dynamic processes. For example, reaction kinetics and study of equilibrium and so on. This is mainly because that when we get NMR spectrum, so the peak width is directly related to the relaxation time of the nuclei that we are dealing with. So therefore, from measuring the peak widths, we can obtain the time information. That means we can study certain reaction kinetics as well as we can study the equilibrium processes. Another major application of NMR spectroscopy is in biology, where three-dimensional information of protein, DNA, RNA, protein DNA complexes, protein ligand complexes. These are all very complex molecules, and these three-dimensional information of these structures can be determined by using NMR spectroscopy. Majorly there are two techniques to determine the three-dimensional structure of a complex molecules. One is the X-ray diffraction technique, the other one is the NMR technique. Even though the X-ray diffraction technique is widely used, but you can find out in the NCBI database where there are roughly about 13,000 protein structure were determined by NMR spectroscopy. This is one of the protein structure, MMP13, very complex protein structure. When it is binding with the ligand, what kind of structure it would have, that was determined by the NMR analysis. And similarly, we can also study using NMR the metabolites. This is very much a useful tool for a typical biochemist, where they will try to understand what kind of metabolites are produced in a given reaction pathway, biological pathway. Last but not least, clinical diagnosis. So NMR has gone to clinical side as well. Just go back and see its initial application was in organic chemistry, but later on it has entered into the biology, and then later finally it has come to the clinical side. As we are aware that MRI imaging technique is widely used technique to find out and differentiate certain defects in small tissues. So these are two human brain images, MRI images are shown here. This is a brief history about NMR. NMR historically started with the Rabi observation on nuclear magnetic resonance of atomic nuclei, and later on the bulk sample it was observed by Felix Bloch and Purcell in 1946, and 1953 Overhauser explained the concept of nuclear Overhauser effect, which is having lot of application in structure determination of proteins. And there was a paradigm shift in 1966 where Ernst and Anderson have developed Fourier transform NMR technique, which is actually significantly cut short the experimental measurement of a NMR spectrum. And in the year 1975, with Zener, Ernst actually developed two-dimensional NMR technique, and 1984 Nicholson actually started using NMR to characterize the metabolites, and 1985 the first protein structure was reported by Uthrik, for which he was later on given Nobel Prize, and three-dimensional NMR was developed in the year 1987, and pulsed field gradients NMR studies were carried out in 1980, and in 1996 and 1997, residual dipolar couplings from partial alignment in liquid crystalline media was studied. In the same year, the uh, people started exploiting NMR in for much bigger molecular structure determination of much bigger molecules, where their size is more than 100 kilodaltons. And in 2000s, dynamic nuclear polarization DNP to enhance the sensitivity and NMR sensitivity was developed. Well, these are some of the people who contributed significantly to the NMR research, and I would say these are the stalwarts in NMR spectroscopy. Of course, they are no more, but their contributions are recognized even now by entire scientific fraternity. Here is the man, Rabi. He was awarded Nobel Prize in 1944 in physics for his first time observation of magnetic resonance in atomic nuclei. And these two persons are Felix Bloch and Purcell. They were awarded again in physics Nobel Prize in 1952, especially for experimental observation of NMR spectrum in bulk molecules like water and ethanol. And here is the man, Richard Ernst. He was from ETH Zurich, Switzerland, and he was awarded the Nobel Prize in Chemistry in 1991, mainly for two techniques. One is NMR, FT-NMR technique, as well as the two-dimensional NMR technique. And these two techniques are considered to be the paradigm shift in the NMR history. Here is the man Wuthrik. He is also from ETH Zurich, Switzerland. He was awarded Nobel Prize in 2002 in chemistry, mainly for three-dimensional structure determination of biological molecules, which are nothing but the protein molecules. And here are the two persons. One is Lauterbach and the other one is Mansfeld. So they were given Nobel Prize in 2003 in medicine discipline, mainly for MRI technique development. This is the first NMR spectrum of water molecule, which was originally recorded by Felix Bloch in 1946. You can find in these are the photographic images where you can find the proton signals, proton resonating signals of water. This is the first NMR spectrum of ethanol molecule, where there are three different peaks are there for ethanol molecules, and each peak represents a magnetically active nuclei. And of course, these initial recordings are totally different than what we obtain NMR spectrum on a modern instrument. And a modern instrument, the same ethanol molecule will give this kind of spectrum. You can find a lot of even fine details. So not only three different type of peaks, but we can also see the splitting pattern, and we can also obtain how many number of protons are there under each peak. Before I conclude my first discussion on NMR introduction, I would like to answer this question: what will be covered in this course? In a nutshell, we will discuss all the theoretical background of NMR spectroscopy, and we will also try to understand the practical applications of NMR spectroscopy, especially with regard to the structure determination of organic molecules. My lectures will follow this order, where initially we will have the complete discussion of NMR spectroscopy and its theoretical principles, and which we will try to apply to certain organic molecules which are known to us, and we'll try to predict the chemical shift values. And later on, we will go to much more complex problems where we will work on the NMR data of unknown molecules, and we will try to interpret the NMR spectral data to the corresponding molecular structures. At the end of my lectures, I shall also cover a couple of CSR problems which were given already in the previous examinations. Aim of my lectures would be twofold. Initially, we will try to predict the NMR chemical shift values of known compounds. For example, if you are working in organic chemistry, you will be starting with a starting material and then you want to reach a particular target molecule through cascade of reactions. And if you want to confirm the each step, the product that is formed or not, the NMR can be used as a tool to confirm whether these intermediate products are formed or not. So this requires prediction of NMR chemical shift values before submitting the sample for NMR analysis, and you can interpret that predicted chemical shift values to the experimentally determined chemical shift values, and you will be able to understand whether the product is formed or not. Secondly, suppose if you are provided with NMR spectral data. This is the modern way of representing the NMR spectral data. So no longer people doesn't provide any NMR spectrum. Instead, it will be provided to you in a running text format. And if you are provided with this kind of data, how to interpret this data to corresponding molecular structure, you will be able to do it at the end of my lectures. So you will learn two things. One is if you are having a NMR spectral data, how to interpret that spectral data to corresponding molecular structure. On the other hand, if you are having already the molecular structure which was already determined by, for example, X-ray diffraction technique, how to confirm further the molecular structure using the NMR spectroscopy, you will be able to understand at the end of this course. So with this, we have come to the conclusion on introduction to NMR. In the next module, we will try to understand the basic theory behind NMR spectroscopy. Thank you for listening.